Section 4.9 and 4.10 in Chapter 4 have to do with oxidation-reduction reactions. An oxidation-reduction reaction can also be called a redox reaction, and these are reactions where electrons are transferred. For example, you could have the reaction of sodium and chlorine. Solid sodium plus gaseous chlorine produces a vigorous reaction that in the end will give us solid sodium chloride. In these reactions, sodium goes from 0 charge to +1 because it has lost an electron, and chlorine goes also from a 0 charge to a negative charge because it gained an electron. When something loses an electron, we say it was oxidized, and when something has gained an electron, we say it was reduced. The best way that I use to remember it is by Leo the lion says grr. For Leo, L-E-O, loses electrons oxidized. For grr, gains electrons reduced, G-E-R. So Leo the lion goes grr, loses electrons oxidized, gains electrons reduced. There are some rules for assigning oxidation states. These, like solubility rules, are something that you're going to have to remember. The oxidation state for an atom in an element, like sodium, is 0. The oxidation state of a monoatomic ion will equal the charge of that ion. In general, oxygen is always -2 when it's in a covalent compound, but if oxygen is in peroxides, it's -1. Hydrogen is usually +1 in covalent compounds. Fluorine is always -1 in compounds. A compound, if we were to add up the oxidation states of all the elements, it will be 0 in a compound. If you have an ion, then the sum of all the oxidation states needs to equal the charge of the ion. Let's look at some examples. Question is, find the oxidation states for each of the elements in the following compounds. The best way to start this first one is by using one that you know. In this situation, oxygen is always -2. Oxygen is -2, and you have 7 of them. That would mean that so far this compound has a charge of -14. Potassium is an alkali metal, so it's usually +1, meaning it's usually going to lose that electron, giving it a positive charge. So it's +1, and there's 2 of them, so that total charge there is +2. If we were to add what we have so far, the -14 from the oxygens and the +2 from the potassiums, we would have -12 left over. So that means this middle element needs to make up for a charge of -12, even though, and we know that the compound total is going to equal 0. So if the charge has to be -12 and there's 2 of them, we can divide 12 by 2, and we know that it has a +6 oxidation state, like so. At this point, pause it and try to do the rest of them. All right, for this next one, we know that oxygen is usually -2. Because there's 3 of them, that gives us a -6 charge. We know that the whole ion carries a charge of -2, so that means that the carbon here has to have a +4 charge. Again, we know for the next one, we know that oxygen is usually -2. That gives us a total charge of -4 since there's 2 of them. So we have to have a +4 on the other. PCl5, chlorine, is almost always -1 because it usually gains 1 electron to fill that outer shell. Because there are 5 of them, that means that total charge there is -5, which means the other part needs to be +5. For the very last one, fluorine is always -1. So that gives us a charge of -4, which means the sulfur will have to carry a charge of +4. Now this is assigning oxidation states for each of the elements in a compound. Just some key points about redox. It always is going to involve a transfer of electrons. Typically that transfer is forming ions, although not always, so this is why you have to be able to calculate the oxidation state, because it's not always going to form an ion. If it is oxidized, that means there is an increase in oxidation state. So it loses electrons. Remember, Leo, the lion, goes gur, so loses electrons, oxidized. Another name for whatever is oxidized is the reducing agent. When you have reduction, there's a decrease in the oxidation state because it has gained electrons. Leo, the lion, goes gur, gains electrons, reduced. Whatever is reduced, we also call the oxidizing agent. And I'm pretty sure that's just to make it complicated. I really don't know why, but that's how it is. So let's look at a sample problem here. Which of the following reactions are oxidation-reduction reactions? Once you have determined which one is an oxidation-reduction reaction, identify the oxidizing agent, or whatever's being reduced, and the reducing agent, so whatever's being oxidized. Okay, so pause it here and look through these electrons. I will tell you that you will have to figure out what the oxidation state is of the elements in the compounds to determine what, if any, electrons are being transferred. Okay, so for this first reaction, reaction A, you have zinc going from a 0 charge, because if it's just hanging out there by itself, it has an oxidation state of 0, right? It's not going to be sharing electrons with anything. And then over here, in the zinc chloride, it's going to have an oxidation state of +2. So it goes from 0 to +2, so it's lost 2 electrons. The HCl is going from a charge of +1 to 0, which means it has gained an electron. So we would say that the hydrogen has been reduced and the zinc has been oxidized. That would make the zinc the reducing agent and the hydrogen, or the HCl, the oxidizing agent. There's another reaction that involves exchange of electrons. Here we have copper chloride, where copper is going from a charge of +1 to a charge of +2, and chlorine going from a charge of -1. Okay, it's still -1 over there. And then, so copper is doing two things. Copper is going from a charge of +1 to a charge of +2, and also to 0. So in this situation, the copper is acting as both the reducing and the oxidizing agent. And that about sums up what you have to do for section 4.9. And that's really being able to assign oxidation states for elements in compounds.